In this video, we're looking at trig induction. Now, this is the one that I find personally the most difficult, but once you've done enough practice at it, you get a bit more used to how they all work. The main thing you'll want to do with trig induction is to keep the SACE formula sheet on you, which has this big list of trig identities on it. You will essentially need these to do trig inductions, and it's mainly a matter of just finding whichever one's appropriate for your situation. Let's get started. So we've got this one here that we're trying to prove with trig induction. I've just done the let Pn be the statement thing. So now what we've got to do is P1. So on our left-hand side of this equation, what we've got is essentially just cos of theta because n equals 1. It's actually not a bad idea to make sure that that is what you get when n equals 1. So here that would be 2 times 1 take 1. So that is cos of theta that we go up to. On our right-hand side, we've got sine of 2 theta over 2 sine of theta. Now, usually what we do is we work from the left-hand side and simplify it down to the right-hand side. But in this case, it's actually going to be a bit easier to work from the messier right-hand side and simplify that to get cos of theta. So we'll need an identity for dealing with sine of 2 theta, and that's going to be this identity right up here. Now, usually you'll have to do some searching for the identities and just find the one that you will find appropriate for your context. There we go. So that is 2 sine of theta cos of theta, and then that's 2 sine of theta. The 2 sine thetas conveniently cancel right off, and we're left with cos theta, which is what we wanted, and therefore we can say that P1 is true. Wonderful. Okay, now we're going to assume that that is true. That's the pk step for some k and z. That's exactly the same as the initial statement, just replacing n with k. Now let's look at our pk plus 1 step. Okay, so on the left-hand side, we're going to have that big sum. So it's cos of theta, cos of 3 theta, goes all the way up to cos of 2k take 1 theta. And because it's the k plus 1th step, we have the extra term. So that's cos of 2 k plus 1 take 1 lots of theta. Wonderful. One more bracket. There we go. Now, let's do our want to show step. So our want to show, or in other words, that is our right-hand side when we let n be k plus 1. So that is sine of 2 lots of k plus 1 theta, and then on the bottom, 2 sine of theta. Now we might simplify that down a little bit after, but I'll just leave it out there for now. Wonderful. Okay, let's continue working with our left-hand side. So we've got that stepped out. As usual with induction, this whole first section is just our star step. So that is sine of 2k theta, all over 2 sine of theta. And then I'm still left with cos of, we can simplify this down a little bit, 2k plus 2 take 1. And then this becomes sine of 2k theta, all over 2 sine theta, plus cos of 2k plus 1 theta. So that's just simplifying again down in the brackets a little bit more. Now, when we deal with fractions like this, usually the step is to cross multiply. So we're going to be timesing by 2 sine theta over 2 sine theta. Now, technically, since this one was over 1, we would times that by 1 over 1, but I'm not really going to bother writing that because it won't do anything. So what that'll achieve is it'll get 2 sine theta on the bottom of the whole thing. And the other reason you might be clued in to do that is because if you look at our want to show, it actually has 2 sine theta on the bottom of the fraction there as well. So that's a good indication we're on the right track. So what we've got here is sine of 2k theta plus, and then this, I'm just going to put the sine theta out the front, and then cos of 2k plus 1 lots of theta. Just like that. Okay, now we need to look for an identity to simplify probably this messy thing on the right-hand side. I will also mention there's usually multiple ways to do these proofs, like multiple identities. The best one that I've found is this other one down here. So it's where we've got 2 sine A cos B. Seems to be a pretty useful one. So just to write that identity, so that is 2 sine A cos B. That is sine of A plus B plus sine of A take B. And in this situation, we're going to have A being theta, and B is 2k plus 1 lots of theta. And that should match everything up to what we've got in this little expression here. Okay, so let's see what we get. So that first term won't change. So this is sine of 2k theta. This one here, so we've got sine of A plus B. So that's going to be theta plus 2k plus 1 lots of theta. And then we've also got sine of A take B. So that's theta take 2k plus 1 theta. Other thing that I'll mention, like how did I know this was the right trig identity to use? A big part of when you're looking for trig identities is you want to show again. So you'll notice in the want to show that we don't have any causes in that. So I was looking for an identity that would get rid of this cos, and that's essentially how I could see that that one might work, because it spits out 2 sines, and then I've gotten rid of all the causes in the expression. Okay, let's see if this would simplify down any further. So this is sine of 2k theta plus, now this becomes sine of, well, if I pull out theta as a common factor, it's going to be theta, and that's essentially 1 plus 2k plus 1. It'll be 2k plus 2 theta in the end. Here, I can do the same exact thing. So sine of theta with 1 take 2k plus 1 all over 2 sine theta. Now, this is going to become sine of 2k theta plus, now this just becomes sine of 2k plus 2 theta, that middle term. And then the last term, if I go 1 take 2k plus 1, that actually becomes sine of minus 2k theta. All right, let's jump back to our want to show now. I'm going to expand that out just so we can compare a bit easier. So that is 2k plus 2 theta over 2 sine theta. Now you might notice here that this want to show essentially matches our middle term. So if I could have just that stuff in yellow, I would have finished the proof. How do we get rid of the other stuff? So with these 2 terms here, it's actually another trig identity that sine of minus x is minus sine of x. So if you want, you can actually add those up to your list here. So that is another one to add. Sine of minus x is minus sine of x. SACE won't put that one on the formula sheet for you. Cos of minus x is positive cos of x. That's the other side of that identity. So those 2 are very useful identities there. Okay, but the point is they cancel out. So I might just say they cancel out, and then we just go in the little curly brackets over here to explain what we're doing, as sine of minus x is minus sine of x. So what are we left with? Well, we're left with sine of 2k plus 2 theta all over 2 sine of theta, which is exactly what I want to show said. Great news. Therefore, pk plus 1 is true. Therefore, by induction, cos of theta plus cos of 3 theta plus all of that should equal, what was it, sine of 2n theta over 2 sine theta. And that's a trig induction. They can show up like this. This is like a trig summation induction. You can see trig matrices, you can see trig products. Pretty much this is just, if they're going to add trig, see if you can find an identity that works. That's the strategy. And of course, don't forget to finish off your proof with these little bits of notation at the end.